We're going to pick up where we last left off on annuities. So last time we started with the introduction of annuities and its unique ability to handle multiple payments or deposits. Or if you're talking about the variables for the actual equation, you will see that I refer to them as recurring payments or reoccurring payments. We'll start off with writing annuities continued. Now with that introduction, we covered only a basis of some of the variables we could solve for, in this case future value and present value. We want to recall those formulas again, and they are the following. Here is the future value formula. I'm going to write down really quick. And again, if for whatever reason people are unfamiliar with this, they can refer to the previous video that I have posted and the present value formula, which again is strikingly familiar, or similar I should say, with a couple of adjustments. Last time on the video, I addressed what these formulas are used for. This time around though, we're going to say that up front so that people have this intuition as to when a problem is asking for a certain context or a certain problem, these will hopefully register immediately in people's minds. In this case, what do we use them for? Using for the following. We'll start with future value first because it's normally the easiest. I'll mark it here, color code them, marking this one in purple. Whenever you're thinking of the following keywords, future value annuity should be coming to head, or to mind I should say. Anything involving investments. So again, these are key words or key hints that you would read on a word problem. Deposits, right? Because if you're depositing something, you're depositing to put something away in the future. Normally, you don't hear deposits as a connotation for owing money. It's for investing money or saving money. Speaking of which, savings. Another example, more real life, is 401k, if you hear that. And the last thing is sometimes people will informally think of the future value as a lump sum that I'm going to put in quotation marks that comes later. What I mean by later is that the lump sum that is accumulating towards via interest as well as the contributions that a person would make. You're building all this money, you're depositing all this money per, whether it's per day, per month, per week, whatever the case may be, so that there's a large amount that you can withdraw, if you will, at the end of maturity or whatever time frame you're in. That's what is meant by lump sum for later, not now, because if it was for now, you would be receiving that money immediately. If it was for later, like these future values, you can always remember in the future. The future is when you're going to have this lump sum. Now speaking of now or in the present value annuity, generally you'll see it for scenarios of loans, car loans, credit card loans, equity loans, mortgages, you can think of this as, I'm going to put in quotation marks, scenarios that you are owing money. And then in terms of lump sum, The lump sum comes now instead of later. So now is the major difference between the future value, which becomes a later, which I suppose I should underline as well. Okay. As mentioned previously, R in both these formulas right here, I'm going to circle it. If you look at the top, between the future value and the present value annuities, R is the only other variable that is solvable for, right? We do have other variables such as the compounding period, the interest rate, the number of compounding periods, or time as I refer to it informally. The thing though is that you can't rearrange these formulas to solve for those variables because it would get terribly messy and the algebra would be very hectic, it'd be very tedious, more tedious than anyone would imagine now. Therefore, as far as this topic is concerned with this class, or at least teaching this class as it is, the only variables we can solve for are, I'm going to do this in a different color here, let's do pink, the present value, the lump sum, future value, which is also a lump sum, or the recurring or reoccurring payments for both these equations, respectively. Now, before we jump into both of these equations that are altered for the R formula, or solving for R, we need to do fractions, or we need to visit fractions really quick. So below, I'm going to write, we're going to pause a moment here, pause for a moment. So that we can revisit everyone's favorite, fractions. Okay. Now, a simple question. This one I'll type out. So how do we solve for x in the following equation? So our example here, e.g., for example, 2 equals x. I know that's weird that I'm putting the variable first, but there's a point to it. x3 over 5. So depending on the strength of your algebra skills or what you recall or whatever your basis is, some people may go about saying, oh, we could divide by 3, for example, and if you divide on one side, you divide the other, and then you also have to multiply by 5, because once you multiply by 5, it gets rid of the denominator, and then you have to multiply 5 on the other side as well. Now, that's if people want to break it down step by step. The only problem is that it can get really messy. However, it does work. The other way to do about this is, normally when there's a fraction involved, I'm going to erase this right here, is that one can use the reciprocal. Remember, the reciprocal is basically the inverted fraction of whatever you're looking for. So for example, the reciprocal of, for example, let's say 3 over yz, it would simply be the opposite, right? yz over 3. So you can see it's the entire opposite or inverse, not a proper inverse, but the numerator and denominator, they switch places, right? Revisiting the example I stated right here, right? Suppose that we solve for x, which I'm going to box in green right here. Okay, we can take the reciprocal, use a different color here, of whatever is being multiplied by that x, in this case 3/5. So the reciprocal of 3/5 is 5 over 3. And then if you remember your fraction game well, you can see that when two fractions are multiplying and they're on opposite sides, they will cancel each other out. However, what you do on one side, you must do on the other side as well. So you have to multiply both sides of the equal sign by 5/3. And basically, this implies that our x is equal to 2 times 5/3. Or if you want to simplify this, it's just 10/3. And then x right there. And that's our answer for this little example. And then as you can see up here as well, the 3's cancel with one another and the 5's cancel. And remember, that's not cross multiplying, that's cross canceling, because you have two fractions that are being either multiplied or divided by one another, generally multiplication. So the key component, or this key concept to take away here or to recall here, is the fact that you can get rid of fractions easily by multiplying by the reciprocal. Now, why is this important? Let's look at the future value formula. So again, I'll write it one more time. I think we have enough space. Now I'll separate it right here. So again, back to annuities. We have the future value formula. Now I'm going to rewrite the formula, and I'm going to give myself a little bit of space, more than usual, so that I can make this very visual and hopefully very apparent as well. Similar to that of the fraction up here that I'm scrolling up to, see the original in black? 2 equals x3 over 5. You can see here that we're going to want to solve for the r here so that we can have a reworked formula. But notice that even though it is a complicated fraction, you still have a numerator and you still have a denominator. Numerator, denominator, I abbreviate those. So you can see what happens is that you're going to need to isolate r or get r by itself, or to cancel such that r is on its own. You have to multiply by the reciprocal. And the reciprocal of this fraction without r is the numerator taking place of the denominator taking place of the numerator. So for visual sake, I'll just draw arrows first to show you where things are going. For example, the denominator, this I over CP, it's going to go right next to the future value in the numerator now. Right, so then we have this now fraction that will now have a numerator of not only the future value, but the future value times the previous denominator, which is the I over CP, or interest rate divided by the compounding period. And then this entire former numerator now goes in the bottom as the denominator. So I know there's a lot of arrows going here and it may look a little messy, but the point is that this implies that our new formula is the following. I'm going to put R sub FV, R sub future value, so you know which one we're talking about it. And it's the future value times I over CP, and then that entire numerator now in the denominator. 1 plus I over CP, and CP minus 1. And here we now have our formula for solving for R, the recurring payments, in a future value scenario. And the variables, they stand for the same exact thing. Again, we just simply rearrange the formula so that we can work with a different scenario. And it turns out, with the same algebra, the present value, which I'm going to write down here, present value reworking that formula in the same exact manner, we get R of PV equals the present value, I over CP. And then now, 1 minus 1 plus I over CP raised to the negative n CP. So you can see I got this equation by using the present value formula and using the same technique of using the reciprocal fraction to isolate R. Again, let me box this one more. So now we have our 4 equations as far as this class is concerned. Our 4 equations involving annuities. Okay? So let's move on to the examples now. We'll start with example 1 here. And again, most of the time, we'll see that the examples are simply just given to you. They're not established in any way or hinted in any way. That's what the students I encourage to decipher the meaning. Again, these notes are going to establish what type of problem it is because for learning purposes. However, when practicing, you'll see that there won't be any hints other than the context of the problem. In other words, example 1 here will be a future value problem and then solving for R. So again, that's what I'm talking about in the sense that it's not going to be given to you. So R and a future value. So here's the problem. Okay? Suppose you want to make $1 million over 20 years at 2% compounded monthly. And the question here is asking how much needs to be deposited each month to make this goal. Now, normally I would like to wait and pause and have students take a moment to figure this out. So since this is a video, the nice thing is that you can actually pause and try to figure out the same hints that I always provide when talking about these finance equations. However, I'm going to jump right into it right now. So what are our key words right here? Well, you know it's compounded monthly. So you know that the compounding period is immediately 12. So again, focusing on the finance tools that one would have going through this class is that they now have a simple interest formula, a compounded formula, or compounding period formula, a compounded continuously, and now annuities. So the fact that you see it says compounded monthly, you know it's either going to be a compounding period problem or an annuity, because those are the only 2 formulas that provide a compounding period. Remember, compounded continuously does not have a compounding period, and simple interest does not have a compounding period. Now, how do you know whether this is one having to do with a regular compounding period or an annuity? And then that is this right here. The second sentence, or the question itself. How much needs to be deposited each month? If it would have said single deposit, then it would have been a compounding period problem. Since this is recurring payments or recurring deposits or deposits that are happening each month, you know immediately that this will be the formula that we just introduced. So it's the annuity solving for R for future value. And it looks like the following. 1 plus I over CP and CP minus 1. Okay, writing down your usual suspects. R for the future value, that is what we're looking for, our monthly deposits. The future value itself is $1 million. I is 2%. But remember, you're going to divide that by the compounding period. As you can see, the equation already has that built in. Still, it's good to talk about that, realizing that, oh, you're going to be taking this, dividing by the CP. And then as I did the previous one, this is 20 years. However, we can knock out this calculation immediately, and it will help us a lot more when we punch in the numbers for the formula. So again, this would be 12 times 20, which is 240. Make sure I'm not making any typos. Plugging this in, it will look like the following. 1 million divided by 0.02 by the compounding period, which is 12. Should have had the number there. And then the rest of this, which is 1 plus 0.02 minus. Now we can write out the calculator syntax and have this written out. Again, it depends on how people go about this in terms of doing their scientific calculator or writing it out. I feel it's relatively easy if you simply take it in 2 steps by calculating the numerator first and then dividing and then using the calculator itself to not necessarily recall but store the previous answer. So here again, I'll write calculator syntax. And step 1 here is one would calculate just the numerator. So that's literally 1 million times 0.02 divided by 12 equal sign, and then this gives us our first sub answer or partial answer. And again, as I alluded to in the previous video, this will give you just the numerator. You're going to leave the answer in the calculator without clearing or anything of that nature. And then that will allow you to do the second part right here. So after the answer is calculated, whether you use your graphing scientific calculator or you're typing it out via a cell phone or on a web browser, you get your answer, and without clearing it, you have to divide, because we're going to divide the whole fraction, and we need 2 sets of parentheses here. One for the entire denominator, and the other for the smaller parentheses inside. And then the rest should be relatively straightforward. 1 plus 0.02 divide by 12, close one parentheses, caret 240. And again, I mentioned this in the previous video as well. You just want to make sure that this becomes a minus, not negative, minus sign, and take it away from the exponent if your calculator does that. And then we need to close our parentheses again, and then equal sign, and then this will give us our proper answer here. Now again, as you can imagine, I did the calculation in advance, but what I got, as long as there's no typos, is the recurring payment for a future value to reach this goal is $3,392.17. Now, as you're thinking about this, you're thinking, wow, that's a really high amount to put away every month. Nearly 3,400. But why is that? The reason is that, in short, we have a low percentage rate, interest rate, 2% growth. So not that great. Yet we still want to make $1 million and we only want to do it over 20 years. So you can see that the time is not particularly long. Granted, 20 years is a long time physically, yet in terms of finance, it's not that long. And we have a really slow growing rate. So how do you compensate for that so that you hit your $1 million goal? And that's to increase the monthly payments. Now moving on to the second example, example 2, and again, this is a present value solving for R as well. And the example will say something such as this. you are loaned $20,000 for university studies. What are the monthly payments for this loan over 30 years at 3.14% compounded monthly? Okay, and this is where you would probably want to pause, try to figure out your keywords, your hints here for the problem itself. Otherwise, here we go. Again, it's compounded monthly. You know that CP is 12, and it's rather obvious with the second sentence. However, still, you are loaned a certain amount already. So if you're already loaned a certain amount, you can't be solving for the present value because that's what you were given up front. You were given $20,000. So here you can see it says, what are the monthly payments? Monthly payments for this loan. So therefore, you know the formula you'll be doing or using is the present value annuity solving for the recurring or reoccurring payments. 1 minus 1 plus ICP negative NCP. And that's, of course, the other thing to be cautious about, that this formula has a negative exponent in both its formulas, whether it's solving for the present value or the recurring payment for a present value. Recurring payment for present value is what you're looking for. The present value itself is $20,000. The interest rate is 0.0314. Again, that's divided by the compounding period. And N is 30 years. However, that's being multiplied by 12 because of the compound monthly, and I'm going to write this number immediately, which is 360. Filling out the formula, you get 20,000, 0.0314. Now we're going to divide by the compounding period, all over 1 minus 1 plus 0.0314 divided by the compounding period again, and this time to the negative 360. That's what your formula looks like. The calculator syntax itself. Syntax itself is similar to that of the future value. I just want to make sure that we have it right. So first, do the first step here for just the numerator. And if you're curious as to why the parentheses are not needed, the calculator knows to go from left to right when it's either multiplication or division. So it knows that, yes, there's a fraction there, but it knows to multiply 20,000 first. So therefore, you can actually do this without any parentheses. Literally type all this in, and then you get the first sub answer. And then the second step, again, remember, don't clear the answer. You're going to reuse it. Divide symbol. You need to open the first set of parentheses, 1 minus, another set of parentheses, 1 plus, 0.0314, divide by the compounding period, close your parentheses, and I'm going to do the same thing here. I'm going to write a caret, and instead of showing the negative symbol or anything of that nature, I'm simply going to write a negative 360 here so people can tell the difference. And then you would close the parenthesis one last time for the denominator, equal sign, and then this gives you the proper answer. Now again, this would be a good moment to practice this to make sure that you have the right answer. But given that I don't have any typos, the recurring payment for this present value or reoccurring payment for this present value, rounding for money, is $85.84. That looks right. At least that's what I have written down. Now, same thing, you want to check yourself. Why is this answer so small, right? Well, it's several reasons, but the two biggest factors are the fact that you're not loaned that much to begin with. 20,000 isn't that lot. Isn't that much, isn't a lot. It is physically, however, in the whole scheme of finances, financial things, it's not that long. And this is a loan that's over 30 years, so quite some time. So there's plenty of time to pay this off, and that's why there's a lower monthly payment. Now, I did do this a lot quicker, however, the formulas are very similar, and that we took the time algebraically to figure out where they came from. They didn't come from thin air, whatever the case may be. They were derived formulas from the annuity equations that we introduced in the last video. So we wrapped up this time around annuities, solving for the R, or recurring payment, reoccurring payment, for both the future value annuity and the present value annuity, using the same hints that we used before. Next is applying these annuities. These annuities are straightforward in terms of questions. The first two examples here, previous two examples in the last video. But now, since we have the mechanism as to how annuities and monthly or some type of periodic payment or deposit works, we can find applications of these annuities. We won't do that now. That'll be for a separate video at another time, but just as a insight or preview of coming attractions, generally you're using annuities for amortization schedules, schedules for mortgages, and for purchasing analysis for certain products as well. Thanks for tuning in.